Welcome back. What we're going to do is pick up with our sheet pile design where we left off at the previous video. We computed our force balances below the excavation bottom and our point J where the tip of the pile will be driven to. So we know that we have this complex pressure distribution, and at this point what we're going to do is we are going to consider the sum of forces and sum of moments. Those are our two equations of equilibrium, and we can use those equations of equilibrium because our sheet pile, once it has allowed the soil behind the excavation to relax a bit, it no longer moves or rotates. So we know that it's at equilibrium and that we can use our sum of forces and sum of moments. If you look at this diagram that you have on the screen right now, hopefully you can see this well. What you have is we know PA, we know PE, we know PA2 and PJ, and we know the depth is 10.5 feet in our example problem. What we don't know is the depth D or the distance to the point of rotation, which we're going to call Z. Now, we don't know those values, but we have two equations of equilibrium and two unknowns. So if we're creative, hopefully we can use those two equations, solve for them simultaneously, and find our unknowns, the depth of the pile and our point of rotation. Now, the depth of the pile is incredibly important because that tells us how long our pile needs to be and how deep we need to drive it. The point Z is actually going to help us with our force balances later on in the problem, so it's going to be valuable, but we need to really solve for D in terms of Z. That's our goal in this portion. Alright, so where we're at right now, if we go through our PowerPoint really quickly, we've got these two unknowns, and our goal, of course, is to sum the forces in the horizontal direction. Our sign convention is going to be using left as positive. Before we get into that, why don't we open up OneNote and we'll actually take a little step here where we take the time to redraw our diagram with our knowns and our important values. That will help us as we go forward through the problem. Okay, so you'll probably get sick of drawing this pressure diagram after you've done enough times, but what we're going to do is we're going to draw this out. That is our original ground surface. Here is our sheet pile, or whatever our cantilever pile might be, and there's the bottom of our excavation. Okay, we know that this value here is going to be 10.5 feet, so we'll label that 10.5 feet. Okay, and if I draw this down a little bit further, what we also know is this point here, PA1, and we know that above PA1 we don't, or from PA1 and above, we don't have any passive pressure. It's all active pressure at this point because we're rotating counterclockwise. All right, so we're rotating in this direction. All right, and our PA1 in this problem we know is 416 pounds per square feet. And if you remember back, if I open this here and scroll up, this is the problem that we are now dealing with. Okay, so let's go back to our drawing here, and the other values that we need to have that you might have seen on the past drawing. All right, we need to know where our point of rotation is. That's going to be a value we're going to label here. We're actually going to carry this down and find PA2. All right, and PA2 we've already computed, and PA2 in terms of D is 40 D plus 416. Again, these are all in pounds per square feet. Okay, now one of the things that we did was we computed what we call P sub E. That is really defined by the line that connects some portion over here on the excavated side, okay, to this value PA. What we know is happening below the bottom of the excavation is that at this point and going down, so this area in here, we know that we still have more active pressure from this point up, okay, than we do passive pressure. But we do also know that the passive pressure overcomes the active pressure much more quickly, meaning that the coefficient is much higher. So there is an actual slope to that line that we're going to deal with later. It's going to be very important. Right? But if we were to continue this line down, kind of a phantom point here, we would end up with what we call P sub E, okay? And that is 320 D minus 416, okay? 416. And that's in pounds per square feet. Now keep in mind we actually don't have that pressure here, but that's what's going to help us define this line later. Now the last value that we need to deal with is what we call P sub j. It's going to go down over here. P sub j is the balance between the active and the passive pressure below the point of rotation. So we have our passive pressure on the retained side and our active pressure on the excavated side. And that came out to be 320 D plus 3780. Make sure that's clear, 3780. Okay, all of this in pounds per square foot. Now, if I draw this kind of clearly, you can see there's a triangle there. We've got a triangle up in here at the top. And so we have a bunch of geometric shapes that we can most likely deal with. Okay, now I'm going to go back to the PowerPoint, and we're going to discuss how to deal with these different shapes and summer forces. Okay, so let's pop this back up. This is where we left off, only we labeled ours with the example problem. So if we go here, up here, we got some of the forces must be 0. Some of the moments must also be 0. So let's deal with the forces first. If you look at this, we know that the forces are related to the pressure diagram. So we're actually going to find the area where the pressures are equal to one another, where the sheet pile is in equilibrium. The reason it doesn't move is that the pressures on the right-hand side, our active and passive pressures, depending on where we're located, must equal the pressures on the left-hand side. That is what we know will have us reach equilibrium. Okay, so let's solve that. Now we know that we have a force here. We have a force here. With that triangle, we've got a force here, and then we've got a force down at the bottom. Okay. Here's our sign convention, to the left being positive, to the right being negative, and a counterclockwise motion is going to be our moment. Okay. It just makes it easier for us to define our reference points that way and our coordinates that way. Okay, so let's sum the forces at h. And it doesn't really matter where we're summing the forces, it really is in the x direction. Okay, so we know we have these triangles, all right? Those are our pressure distributions, and we have these lines extended that will actually help us simplify the problem. Okay, they really do nothing more than simplify the problem. Your bold lines are what your actual pressure distribution boundaries are. The dashed lines are kind of these phantom values that allow us to simplify with geometry a little bit better. Okay, the first triangle we're going to deal with is HPA over 2. Okay, that's this top triangle. I'm going to highlight it. That is the height times the base there, which is P sub A. That's the active pressure along the plane B. Divide that by 2, and that gives us the area. Now, you should look at this and say that's a very easy one to calculate. Okay, and it is. But as we go a little bit deeper, it's going to be difficult for us to compute perhaps the next triangle down, right? We know the PA is going to be the base of that triangle, but we really don't know where that crosses the plane of the sheet pile. Okay. Similarly, we don't know what point Z is, we don't know the depth, and we also don't know any of these other boundaries. So what we're going to do is we're going to simplify and use what we do know to do the computations. Okay. Another shape that we can find is this trapezoid. Okay. Now you look at this and you say, well, that's not a pressure distribution, and you're right, it's not. But what it does is it does contain two portions of the pressure diagram that we need to account for. So follow with me here. This is a simplification, and hopefully you'll understand it after going through it a couple of times. If we account for this trapezoid, very easy, it's PA plus PA2 divided by 2. That's the average between them. Multiply that by the depth, D, and that gives us the area of that trapezoid. Pretty simple. But the issue is we've accounted for one. That's great, one of those triangles that we would have otherwise had a difficult time with. The other is we've accounted for this very odd shape down here, and that's, you know, another very good thing, because that would be hard to account for also. But the other problem is we've counted a section that doesn't have a force, and that's a little weird, right? If you stick with me here, what we'll do is we'll actually try to subtract that out later. Okay, so right now with the two terms that we have above, you've computed the area of all of this triangle, all of this area below here below PA. Next, let's take a look at this triangle here. Again, it's easy to compute. It's just going to be PE plus PJ, that's the base, times Z over 2. That's what you're going to see there. And here, again, we've accounted for an area that we need to, that's important, right? That would be difficult otherwise. We've double counted an area now. That's not very good. And we have accounted for another area that doesn't exist. So at this time, we're kind of at a strange point where we've accounted for a couple of areas that don't exist. We've double counted an area. But what we can do, a really nice, elegant solution to this, and the reason we do this process the way we do, is we consider this triangle here. Now, keep in mind the triangle on the left-hand side of our sheet pile really must balance out the area of the triangles on the other sides. Now, the way that this is drawn is not very good in terms of scale, right? Because we can see that that triangle does not balance the other triangles in terms of size. However, we know that it must in order for this to reach equilibrium. Okay, so since that's a negative force, the way that we've defined it, if we subtract this triangle, okay, we subtract, and the base of that triangle is PE plus PJ, okay, I'm sorry, PE plus PA2 times D over 2, all right. What we've then done is we have subtracted that force, that phantom force that didn't exist, right, that we counted. We have subtracted this other force down here that really didn't exist in that area. We've taken away one of the ones we've double counted, and because this is negative, we've now appropriately accounted for this other shape over here. Okay, so that's a negative force. What we end up with is accounting for all of the areas we need to with these 4 simple expressions. All right, what we'll do here is we are going to, what I'm not going to do is write this out for you, because we can go to our example problem. If I open up our example problem, you can do all of this in terms of the values you're given here. More importantly, you can do it in terms of PA1, PA2, PJ, PE, D, and Z, which we can label. Why don't we label D and Z? D is going to be this depth here, extend that a little bit further, and Z is going to be here. Okay, we can do exactly what we just set out to by plugging our sum of forces equation, or our values in here for our sum of forces equation, make sure it equals 0. And what we're going to do once we get to that point, all right, so our sum of forces is going to equal 0. If we go back to this, you should be able to solve that. That is this area here. Sum of forces equals 0. We're going to add those all up, set it equal to 0. Okay, but what we now need to do once we have put that equation together is we need to solve for Z in terms of D. All right, and the reason we do that is we have our unknowns Z and D, and we know we need to do a substitution in order to solve our simultaneous equations. So when you use your sum of forces equals 0, you plug all your values in, you should have that in terms of D and in terms of Z. Those are going to be your 2 unknowns in that equation. And what you're going to ultimately do is solve that equation for Z, and what you'll end up with as a check is Z equals 80 D squared plus 208D minus 1092 all over 160D plus 841. My suggestion here for you now is to take a moment, play around with your calculator, put your sum of forces, whoa, that was really bad, to put your sum of forces in the x direction equals 0, solve that out using these values that we just highlighted, and simplify that equation, and you should end up with Z equals this expression. And that we're going to use a little bit later. In order to solve our simultaneous equation, we need to also deal with our moments, and so we're going to do that really quickly here also. Okay, so once you've solved for z in terms of d, and I would pause the video until you've done that, then we're going to deal with our moments. Now the moments are actually quite easy now that we know these shapes. We're going to sum the moments about this point f, and this point f, if you look at the bottom of the pile, down at the bottom of z on plane j, you'll see this point f. F is what we are going to be summing our moments about. We're going to sum about that point, and when we have our sum of moments equals 0 equation with all of our values in here, hopefully they'll be in terms of d and z, and we can do a simple substitution to find out what d and z are by solving our simultaneous equations. So let's take a look at this. Again, let's start with the easiest shape. That's going to be this triangle. And you'll see the expression I just put up here. What we need to do is find the area of that triangle and the resulting distance relative to f. And so what you see here is the area of that triangle. It's very simple. It's going to be PA times h over 2. And the distance of the centroid of that force, which you'll see here, is going to be h over 3, so 1/3 h from the bottom of plane B, but also a distance d away. Now you see my convention here. I've got the squiggly brackets encapsulating the force, and the square brackets containing the distance. And I'll keep that notation, that way it will make it simpler for you. Okay, so you've got a force and a distance here. That's our first moment. The second moment is actually a little bit tricky because we don't want to account for those triangles. The trapezoid is actually difficult to compute in terms of what the centroid is. So what we're going to do is we're going to break that trapezoid up into a rectangle and a triangle. All right, now the rectangle, very easy to calculate the area of that. It's going to be PA times D over 2. Oh, sorry, PA times D. We don't need to divide it by 2. So PA times D, and the distance that we're going to be away from F is simply going to be D over 2. So we've got a force, PAD, and a distance, D over 2. Okay. Now again, we've accounted for areas that don't exist. We've accounted for that one triangle and then a little trapezoid piece of the bottom triangle. Okay. That means we need to account for this triangle here that was part of our original trapezoid from our other approach. This is actually a very easy triangle to find the area of. It's going to be PA2 minus PA, okay, over 2 times D. All right, and then the distance here, so this is the area PA2 minus PA, that's the base of that triangle, D over 2, PA plus PA1 over 2 times D is another way of looking at that, and then the distance is going to be D over 3 from that point F. Okay. Once we've accounted for that, we've actually have the same check marks that we were used to in the sum of the forces. So we're going to deal with that same large base triangle down here, where we have a base of PE plus PJ and a height Z, so it's going to be PE plus PJ times Z over 2. And then the distance that centroid is from point F is going to be Z over 3. Okay, so we've accounted for that area of the triangle that doesn't exist. We double counted, and then we got that extreme piece on the right there. Now to end this all out, our fifth term here, we're simply going to subtract out the moment that exists from this triangle here. The base of that triangle is going to be PE plus PA2. The height is going to be D, so it's going to be PE plus PA2 times D over 2. That's going to be the force, and then the distance of that force from that reference point F is going to be D over 3. Now, if we go back here, this is quite quick, I understand, so you can always rewind. If we go back to our drawing that we started this video with, go to OneNote here, if it's going to cooperate. We can put these values that we have here, PA1, PE, PA2, PJ, D, and Z, into our sum of moments equation. And when we do that, we have our sum of forces equals 0, which we have converted into this expression here so that we solve for Z. Then we have our sum of the moments, okay, equal to 0, and that's in terms of D and Z. And all we need to now do is take our Z equation, pop it in, and replace it with replace z with our z equation here. Everything is in terms of d, which is set to equal to 0, and we can solve the simultaneous equations. Now I'm going to leave that up to you. It takes a little bit of practice, a little bit of frustration, maybe punching it into the calculator. But when you have indeed done that, solved your simultaneous equations, okay, your sum of forces and your sum of moments, you will end up with a depth here in this problem of 10.48 feet and a z distance of 2.19 feet. Now, to make it simpler, you might want to use Excel with this and do goal seek, okay? Because solving simultaneous equations in a TI-89 or something even more basic than that is actually a little bit painful and monotonous and cumbersome. So I would recommend using Excel if you can to make that process a little bit simpler. You just have to put this expression in, and then your sum of moments, use goal seek, and then you can come up with your answer. Okay? So at this point we know our depth, about 10.5 feet of driven depth. That's great to know. Now our next step is to understand whether or not our sheet pile or our cantilever pile system will be able to withstand the moments that it's subjected to within the profile of the pile itself. So we're going to pick up the next section looking for the maximum moment, and then we'll wrap up the problem. So check in for the next video.